Hi, and welcome to Chegg's live general chemistry study session. We are here weekly at 8:30 p.m. every Monday night, so put it on your calendar, and I hope to see you here next week. My name is Corinne. I run Chem with Corinne. I am a chemist. I have a couple degrees in chemistry. I loved it so much that I decided to become a chemistry teacher, and I've been embarrassing myself here on social media for many years now. So I'm excited to be here with you all tonight. The goal of these sessions is just to help as many students as possible. So please be active in that chat. Please share this feed. And Chegg is live 11 times a week right now because Chegg is here just to help you out. If you haven't checked out their study resources, please do so. They're also running a special right now. If you use the code Chegg Live 50, you'll get 50% off your first month. I'm telling you, it is absolutely worth it. Not only are they going to show you the answers to those questions that you're stuck on, you're actually going to learn as you're going through their resources. So please check them out. All right, so what we're going to do is we're going to get started with some equilibrium tonight based on your request last week. So again, this session is based on what you need. So go ahead and start putting those questions in the chat, and I'll be going through the chat for the next hour as we work our way through just Gen Chem. And if you're not here for Gen Chem, check out Chegg's YouTube channel. You can see all of the recordings from previous lives, as well as their schedule for the week. So let's say you're taking Orgo right now. Tomorrow night's session is Orgo. So definitely check those out. All right, so let's get started with some Gen Chem. So we're going to talk equilibrium. And for something that's supposed to be all about balance and whatnot, it can make you feel so unbalanced and so confused. But let's just talk through. So we're going to start with just a rice or an ice table example so you can see how we figure out those equilibrium concentrations, because that is the hardest aspect of equilibrium, is kind of knowing where to start. All right, so let's say I have this reaction here. So with equilibrium, you're going to have reversible reactions. You'll see that double arrow. Believe it or not, most chemical reactions are reversible. But in this example, we have phosphorus trichloride reacting with chlorine gas to create phosphorus pentachloride. So let's look at this. We're given our initial moles of each reactant. We're given our equilibrium concentration of our PCl5. And we want to figure out what those equilibrium concentrations are going to be. Let's say we're going to take this one step further and we want to graph it. We need to figure out what those equilibrium concentrations are first. So let's go ahead and do that rice table. I like using rice as my acronym, so I remember to put my reaction on top. And that's just going to help you stay organized with this, because that is so important with this process. And I feel like I say this a lot, but the more of these tables that you do, the more intuitive it is, especially with these ones where it's just a 1-to-1 ratio. It makes it a lot simpler. All right, so I know I have 0.6 moles of this, 0.7 moles of that, but I'm trying to figure out concentration, right? You're also given your volume. So this is in a 1 liter evacuated flask. Makes it really easy, right? If we're doing our molarity calculation, in this case, moles per liter, it's just 1 liter. So this is a 0.6 molar solution as our initial concentration versus a 0.7 molar solution. This is not a situation where we have a common ion. We're not doing this in a certain solution. So therefore, you can assume that the concentration of our product is 0 initially. So now I'm going to subtract X from this, because as the reaction continues, I'm going to be forming product, right, is what we'd expect to happen. Again, I don't have any coefficients in this balanced equation, so it's just a 1-to-1 ratio. So I'm going to subtract X from each of my reactants, add X to my products, and then go from there. So normally we'd say, okay, this is 0.6 minus X, that's 0.7 minus X, and this is just equal to X. But we're given this equilibrium concentration of our product. So keep track of everything you're given in your problem, because this is how we're actually going to be able to figure everything out. All right, so this is my equilibrium concentration of that phosphorus pentachloride, and that's going to be equal to X. So now I know this at equilibrium is going to be 0.6, my initial concentration, minus X. That's just minus that 0.04. So this becomes a concentration of 0.56 molar. That is going to be 0.66 molar. All right, so now I have all of my equilibrium concentrations, and if I want to take this one step further and graph it, I'm going to squeeze that in on this side. Basically, what we're going to do is we're going to have our concentration on our y-axis. And again, we're doing this in molarity, versus we're going to have our time on our x. All right, so we know that, let's go ahead and I'll do them in different colors so you can see each of these. So we want to do the concentration of each. We know our max concentration was 0.7. I'm not really going to have room for this, am I? I'm just going to put it on the wrong side. It will be fine. 50.40. All right. Not the best graph. Don't judge me for it. We're just trying to get through these questions. Okay, so I want to start with when you're doing these graphs, there are a couple things you need to pay attention to. You need to know your initial concentration. You need to know the concentration at equilibrium. And you want to make sure that all of your peaks reach equilibrium or that linear, right, that slope of 0 at the same point on your curve. All right, so I'm going to start with PCl5. Let's do that in pink. All right, so PCl5 at time 0, we had a concentration of 0 versus at equilibrium. Let's say equilibrium happens about this time. We are at 0.4. All right, so not the best graph here. Let me fix that. All right, so if you're just joining now, don't judge me on my graphing ability, but we are just showing the equilibrium concentrations, just telling you how to draw these curves. All right, so we have our initial, we have our final concentration. We're going to do the same thing with our other two species in this reaction. We have our PCl3, phosphorus trichloride, starts at 0.6. We want to make sure it hits equilibrium at about the same point, right, which we say is actually about here, where we have that flat or linear line. And then we are ending at 0.56. So this one is just going to look like this. And then let's go ahead and do chlorine as well. All right, so chlorine starts at 7, ends at 0.66, just like that. All right, again, not the best graph, but what you need to do when you are graphing equilibrium concentrations, number one, you got to find that concentration at equilibrium. You need to have the initial concentration, you need to have the final concentration. And again, you want to make sure everything reaches equilibrium at the same point. Because again, equilibrium by definition is the point at which the concentrations are no longer changing. It's not that they have equal amounts or equal concentrations. They are not equal. It's just you reach this point where your overall concentrations are not changing. So that's what we're looking for. We're looking for that linear portion of the graph where the slope is 0. All right, so that was just a little bit about equilibrium. Let's continue on. So goal of these sessions is to help as many students in Gen Chem as possible. Let me know what you need to work on, and we will go from there. So that was just a little bit of equilibrium. Let's say, I don't know, why don't we look at this reaction further? Let's talk Lewis dot and molecular geometry. So if we look at PCl3 versus PCl5, so looking at these two compounds, right, we have phosphorus trichloride and phosphorus pentachloride. Let's go ahead and we'll write out those names. So if you're working on nomenclature right now, these are both covalent compounds. We're going to use the prefixes to denote the number of atoms that we have in each of these compounds. So this would be phosphorus pentachloride because we have 5 atoms of chlorine versus phosphorus trichloride. All right, when drawing Lewis dot structures, and if you're trying to predict geometry, I'm sorry, but you have to draw those Lewis dot structures. You're going to count the total number of valence electrons in each of your compounds first. This is going to serve as like a way to double check your work, and also it's going to help you if you're trying to figure out double or triple bonds, things like that. So let's go ahead and do that. So phosphorus is going to have 5 valence. So total valence. There are 3 atoms of chlorine in this one. Each atom of chlorine has 7. So that's 21, 26 total valence electrons versus phosphorus trichloride. Again, we'll have 5 for phosphorus and then 35 in that chlorine atom. So we'll have 40 electrons to place for phosphorus pentachloride. So now let's go ahead and look at that and say, okay, let's go ahead and just draw what we call a skeleton structure where you kind of predict how everything's going to come together. So I'm going to put phosphorus in the center. And then I have 5 atoms of chlorine on this one that I'm going to place around that. So that is step 2. So step 1, we counted the total valence. Step 2, we drew a skeleton structure. And then step 3, we're going to add in the lone pairs on the outer atoms. And then we'll go back in and double check our total after that to see if we need any double bonds or any lone pairs on that central atom. So I'm just going to make sure everything satisfies the octet rule. making sure that each of my chlorine atoms has 8 total electrons. Each bond represents the shared 2 electrons. Therefore, each of these chlorine atoms needs an additional 3 pairs of electrons. So an additional 6 electrons. So now let's double check our count. All right, so again, we counted our total valence, we drew out a skeleton structure, we added electrons to make sure everything satisfies the octet rule. Now we're going to go back to that initial total and make sure we have shown all of the electrons in these compounds. All right, so I have 8, 16, 24. I am missing 2. Where am I going to put those 2? Always on that central atom. All right, so now we have drawn the correct Lewis structure for phosphorus trichloride. Let's double check the phosphorus pentachloride now. So I have 8, 16, 24, 32, 40. So that one checks out. I don't need any extra lone pairs. And this is going to change how the geometry is. All right, so now let's take that Lewis structure and translate that into geometry. And with the geometry, the reason I said you have to draw a Lewis structure is because the actual geometry of the molecule is based solely on that central atom. How many bonds, how many lone pairs does that central atom have on it? Because that's going to be what distorts the different bonds. Because again, everything wants to be as far away from everything else as possible. And that's what's going on here. All right, so molecular geometry in this case, right, I have 3 bonds plus a lone pair. This is going to be trigonal pyramidal. And I do have my model kit, so I'll pull those out so everyone can see as well. All right, so trigonal pyramidal, you have that pyramid base. Essentially, you're just imagining that your electrons, your lone pair is hanging out on top. And believe it or not, the electrons actually take up more space than the bonded atoms. So this is what's going to force it into that pyramid-like shape. All right, versus this one, I have phosphorus with 5 bonds to it. Just 5 bonds. I don't have any lone pairs on that central atom, so I'm not going to have one of the octahedral geometries. This is going to be trigonal bipyramidal. Let's see. So again, the solid line represents an atom coming out towards you. We're just trying to show the 3D shape. I am not the best at drawing the ones with the expanded octets, but you kind of see what that looks like. And in case you cannot see what that shape looks like based on my drawing, I do have the shapes ready. Let's see. All right, so trigonal pyramidal, you're going to see that pyramid-like base. Kind of looks like a tripod, right, without the camera on top, versus the trigonal bipyramidal. Let's double check. Nope, this is the wrong one. Sorry. Trigonal bipyramidal. I just showed you octahedral. This is going to be the one that has 5 bonds to that central atom. So this would represent the phosphorus pentachloride versus phosphorus trichloride. And everyone wants to know, like, okay, what's the difference between trigonal pyramidal versus trigonal planar? This is the difference. So if you look at this, you can see that tripod base versus the trigonal planar, everything is within one plane. That is the difference. So 3 bonds versus that lone pair. So everyone likes to say, oh, why does that lone pair matter? Because it completely changes the geometry, the shape of that molecule, because those electrons are really, really important. All right, so that's enough about geometry and Lewis dot structures. It looks like you guys are in the chat. Let me check it out, see what you guys want to go through. I do not do organic tonight, but if you come back tomorrow night, we do have an organic session every Tuesday. So definitely check it out. Head to the YouTube channel now. All of the previous lives are there. You can check those out and hopefully get some help with Orgo. And then let's see, can you go over a stoichiometry? So we have a question off YouTube. Stoichiometry problem with percent yield. Yes, absolutely. Let's do that next. Let's see. And actually, if you are doing stoichiometry right now, I know Chegg does have a dedicated stoichiometry session every Wednesday as well. So like I said earlier in this session, like Chegg is here to help you out. If you are not taking advantage of these sessions, you absolutely need to. It's really, really valuable. And I love that they are weekly. They're at dedicated times. And again, if you missed the session, everything is posted on YouTube now, which is really convenient because you can go right back in, jump in, listen to the question that you need for whichever topic you're studying, and be ready for the next week. All right, so stoichiometry with percent yield. Let's see what I can make up on the spot. Let's see. You know what? Let's do one related to cellular respiration. All right, so in cellular respiration, we have glucose, C6H12O6, reacting with oxygen to form CO2, water, and energy, right? So with this, what we want to do, let's say, and you know what, I'm going to throw in limiting reactant as well, so we get just that extra practice with Stoich while we're going through this. So what mass, question is, what mass of CO2 will be released if 12.5 grams of glucose reacts with, I don't know, 6 liters of O2. So this will just be a really good practice with theoretical yield, and then I'll also talk through percent yield right after this. All right, so looking at this, what do you need to do first with Stoich? You always have to start by balancing your reaction. So this is an example of a combustion reaction. We need to start, I recommend starting with hydrogen because it has the highest subscript. So let's start there. Hydrogen, we have 12 atoms of hydrogen here. We need to make this 12. We're going to put a 6 in front of that. Now do carbon, because oxygen is in every single one of these species. So let's go ahead and balance out our carbon. So we're going to put a 6 in front of carbon. Now we can go back and look at oxygen. So on my product side, I have 6 times 2, that gives me 12, plus another 6 gives me 18. But be careful, because I also have oxygen here. So from that 18, I'm going to subtract 6. That means this has to be equal to 12. So this is going to be a 6, and now this is balanced. So with Stoich, I recommend putting the masses in underneath the species you're working with, just to try to keep things organized. So if I have 12.5 grams of glucose and I have 6 liters of oxygen, how much CO2 am I going to make? And it's actually asking for grams. I probably should have made that liters when I made this problem up, but this will be okay. All right, so what we have to do whenever you're working through a stoichiometry problem, right? You can never compare things on grams to grams or grams to liters basis. It always has to be a mole to mole basis. So your first step is always to convert whatever you have to moles. Once you have something in moles, then I can say, okay, for every 1 mole of glucose, I will form 6 moles of CO2. And it doesn't just have to be reactants to products. You could say, oh, how much oxygen do I need to react with this to react perfectly? And it would be a 1:6 ratio. So we use all these ratios from the balanced equation to make all kinds of really important predictions. Yeah. All right. And it looks like someone jumped on and is balancing it. Yeah. Awesome. Okay. So good work, guys. Yeah, so cellular respiration, this is one that you're probably really familiar with too. But yeah, good work. I love seeing the chat being active, guys. That's what this session is made for. Keep putting your questions in there. If you're not working on stoichiometry right now, put your question in there anywhere, and I will try to get to it as soon as I can. We are here for an hour every Monday. All right, so let's go ahead and just start doing the Stoich. So I have 12.5 grams of glucose, C6H12O6. So my first step is always going to be to convert this from grams into moles. I'm not going to worry about molar mass right now. I'm just going to worry about putting in my units. So I want this to cancel out. So I'm going to put it in the opposite side. So whatever's in the numerator goes to the denominator. Whatever I'm trying to convert into goes in the opposite spot. All right, so I'm going to use my molar mass here. Then I'm going to convert from moles of glucose into whatever I'm looking for, into moles of CO2. Last step, I don't want my answer in moles, I want it in grams. So I'm going to convert from moles of CO2 into grams of CO2. And there's a good chance you may have learned this. It may look slightly different. So this is called, there are different methods, right? You can also draw this with parentheses. But essentially, if you just imagine there's like a multiplication sign in between each of these, right at each of those vertical bars, that's basically how we're setting this up. All right, so now let's go in and fill in everything that I need. It's really easy to do the moles to moles because we're just using stoichiometry. I don't have a coefficient written in front of this, so it's assumed 1. So it's a 1:6 ratio here. And then I just have to go to my periodic table, add up my molar masses. what is that going to be for glucose? So I just have my 6 atoms of carbon, 12 atoms of hydrogen, 6 atoms of oxygen, gives me 180.162 grams in 1 mole. I should have written C6H12O6 there so you could track that. Sorry, I didn't do that. I get too excited and I don't always write out everything. All right, versus CO2, 2 atoms of oxygen at 32 plus 12 for carbon. This is going to be 44.01 grams. All right, so I have set this up to predict how much CO2 I'm going to make based on my 12.5 grams of glucose. So you have a couple options. You can multiply by everything in the numerator, divide by everything in the denominator, or you can take it like step by step. Every time you see a vertical line, that's like another step. So 12.5 divided by 180.162 times 6 times 44.01. Try it out and see what you get. All right, so I got 18.321 grams of CO2. So this is the point now where you're like, oh, wait, sig figs, right? You want to go back into your initial values. This number, mass has 3 sig figs, but because our volume only had 2, technically our final answer will also only have 2 sig figs. So really we'd say this is about 18 grams. All right, but this is only half of the problem. So because I gave you both of the reactants, we don't know which one is going to limit the overall outcome of the reaction. So now we have to take our volume of oxygen and go through the same process to predict how much CO2 we need to make. Technically, all you need to do when determining the limiting reactant is you could stop it right here. Predict the moles that each of these will make. Whichever makes fewer moles of CO2 will be your limiting reactant. Then you can take that and figure out the theoretical yield. I just decided to work out the whole problem though, so you could see it. All right, let's do the same thing with oxygen. Oxygen is going to be slightly different because I started with liters. So with this, you have to remember, we're going to assume that this is at standard temperature and pressure conditions. So we're going to divide by 22.4 liters because any gas at those standard temperatures, at those standard conditions, is going to have a volume of 22.4 liters. All right, so we divide by that. Again, we're going to use the molar ratios. It's 6 to 6. For every 6 moles of oxygen, I will produce 6 moles of CO2, which is equivalent to 1 to 1, right? I tell my students, like, just go ahead and put in those 6s just so you get in the habit of always including that step, right? You don't want to forget to include that step. So let's just continue. Let's just put that there. And then last step, we're basically going to take this last step from the previous one and just put that in that same spot. All right, let's go ahead and calculate that, see which one is our limiting reactant. So that gives me 11.79 grams of CO2. All right, so now the question is, which one is our limiting reactant? Which one? How do we know? It's going to be the oxygen. Okay, 6 liters seems like a lot more than 12.5 grams, right? And it is. It totally is. But you can't look at the initial amounts of each of your reactants and use that to actually make a prediction about the limiting reactant. You have to actually go through this process. All right, so I promised I would do percent yield next. So let's say this is called our theoretical yield. So we'd say this is our limiting reactant. This is what's going to limit the overall outcome versus this is our excess reactant. It's what we're going to have left over. And you can use stoichiometry to figure out exactly how much you'll have left over. Just go through the process. 6 liters will need or require how much of our glucose, and then you subtract whatever that value is from 12.5 to see how much you'd have in excess. All right, so this is our theoretical yield. Let's say in the lab, you had a result of, I don't know, 8.20 grams of CO2. I don't really know how you'd measure that, but this is not the best example of that. Let's say we wanted to calculate our percent yield. if experimental yield was 8.50 grams of CO2. All right, so let's say you found a way, you calculated the volume and then went from there to grams. It can be done, but it just wouldn't happen in a Gen Chem lab. We're just going to make magic happen. Let's go ahead and just practice calculating percent yield. So percent yield is always going to be your experimental compared to the theoretical. Times 100. So how much did you get in the lab compared to how much you were supposed to get using stoichiometry? So whenever you use the periodic table and you do a calculation on your own, that's going to be the theoretical yield. What's going to happen in an ideal situation where the reaction goes perfectly to plan? It's not going to happen like that, right? There are going to be times in lab where you measure something and it's wet and all of a sudden you have a 400% yield. Could that happen? Could you make 4 times as much of something as you're supposed to? No, but there are errors in the lab. So all I'm going to do is I'm just going to plug these values in. Remember, all you have to remember is that it's always your experimental over your theoretical. I guess technically I should have 2 sig figs, so we'll just change that to 12. Your units are going to cancel out. You just change that into a percentage and divide that out. So we have 8.5 divided by 12. That gives us a percent yield of 70.8. So not terrible. You ideally want a pretty high yield, but you want a low percent error. Yeah. All right, let me jump into the chat and see what other questions we have tonight. Let's see. Yeah, it looks like, okay, so it looks like from Chegg's YouTube channel, what are the most important aspects of thermochemistry that I should know? Yeah, that's kind of a big question. So with thermo, you want to make sure you are really comfortable with all of your equations, all of your constants, all of the units, and converting between those units. And I would think like one of the biggest things with thermo is keeping track of your signs, right? So if you're doing that calorimetry problem, making sure that you're aware, okay, which one is losing heat, which one is gaining heat, how is heat moving in this system, just being really aware of that. Also being careful with your different enthalpy equations, recognizing that most of the times it's products minus reactants, unless you're looking at bond enthalpies. When it comes to bond enthalpies, things are flipped. You're going to be looking at the energy of the bonds breaking, which is technically your reactants, compared to the bonds being formed, which would be your products. So just be careful with that. I think that answers that. If that doesn't help, please put more in the chat and I will come back to that. We could probably do an example too. All right. Yeah, okay. Another one on YouTube. Explain Bronsted-Lowry acids and bases. So with the different definitions of acids and bases, you have to memorize them. So with this, you have the Bronsted-Lowry, you have the Lewis, you have the just slightly different, right? But the concept is exactly the same. An acid is going to be something that donates a proton versus a base is what receives it. And how about I put just an example? Again, this is just explain Bronsted-Lowry acids and bases. Let's just do like an example acid-base reaction. And you know what? I think someone else was asking about acid-base chem. So we'll just like roll right into that. So let's talk basics. And then for the person on Instagram who is struggling with acids and bases, everyone is struggling with acids and bases right now. It is the hardest concept in Gen Chem or AP Chem, whatever chemistry class you're taking. Acid-base chemistry is the one that still like makes your professor scratch their heads too. All right, so I'm just going to write out an acid-base equation, and then we'll talk through the different components. And eventually, I'll get better about not like squeezing my reaction into the small part of the board. I feel like it's just a struggle, especially with these long reactions. I need to be better about that. So I apologize for that. So when we are trying to identify the acid versus the base, what you want to imagine is that there's just like this moving proton. And when I say proton, I mean, you're going to watch for the H plus. And that's half of the battle in Gen Chem, right? Is all of the different ways that chemistry teachers and chemists refer to the same exact thing. So if you see the word proton, know that you're looking for that H plus ion or hydrogen with a charge of positive 1. So looking at this reaction, what changes from our reactants to our products is this gains an H plus, right? So when H2O, basically this comes off, joins water, forming H3O. Because I've added that +1, now H3O is going to have a charge of +1. When the H pops off of our acid, it's going to be left with one less of the charge, right? So you're just adding and subtracting based on the number of H's that are being gained or lost. So this is going to be our acid because it donates a proton versus this is going to be our base because it accepts that proton. If you're looking at those conjugate acid-base pairs, the acid becomes the conjugate base. After it loses that proton, the base becomes the conjugate acid. If you're thinking about an acid-base reaction as being a reversible reaction, it's really easy to double check that. Your conjugate acid in the reverse reaction is going to act as an acid, right? It's going to give up its H, becoming the base. The conjugate base is going to gain an H, becoming that acid. So just a little bit about the basics of acid-base chemistry. Let's see. Let me jump on. Okay, it looks like struggling with acid and base titrations. Yeah. So let's just do let's do a sample problem, and then I'll talk through the basics of titrations and titration curves. So let's look at just like an acid base. Let's use this reaction. All right, so this is actually acetic acid, commonly known as vinegar. So let's say we have, I don't know. All right, if the pKa let's figure out the pH. Yeah. All right. All right, you take Chem 1 and you see acid-base chemistry and you get excited. You get excited for titrations because you're just looking for a cool color change and hoping that you add exactly enough that you need, right? Without anything happening, without you overshooting that endpoint. And then you get into Gen Chem and AP Chem and you're like, acid-base chemistry is so complicated. But I promise it's not as intimidating. Yes, it's not as fun as just looking at those color changes and whatnot. You're not just doing strong acid, strong base titrations. But with a little bit of practice and a little bit of exposure to the different types of titrations, it's not as intimidating as it initially looks. So let's just talk through these calculations because these are the types of calculations that you would need. This would be, let's say we're working with a weak acid like acetic acid. These are the types of calculations you would need to go back and forth. All right. And thank you for the person on TikTok. I'm glad you're here this semester. Keep spreading the word, guys. We are here every week, same time, same place. And if you miss this session, maybe you're watching the YouTube replay now, know that you can find everything on Chegg's YouTube. So Chegg really wants to help you out this semester. There are 11 of these sessions each week with teachers like me who are excited to be here, who want to help as many students as possible and want to answer your questions. So keep putting those questions in the chat. If I don't get to them tonight, I will be saving those for next week. So, all right. Acid-base titrations. So if the pKa of acetic acid is 4.76, determine the pH of a 0.20 molar solution. So with these, it's really hard to even know, like, where do I start? You always want to start with that dissociation equation. So what's happening in solution is really important to keep track of. So sometimes you're not given that in the problem. We had already written this out because we were talking about definitions of acids and bases, but that's where I would always start. Write out that dissociation equation so you have it and you can keep track of it. So let's go ahead and determine the Ka first. And again, this is one of those things where it just feels it feels exponentially harder when you're not in Chem 1, because in Chem 1, you're only doing pH and H plus and OH and maybe OH minus, right? The concentrations. It's still the same process, okay? So the pKa is equal to the negative log of the Ka. Looks really similar, right? pH is the negative log of H plus. All right, so when we're looking at these acid dissociation constants, know that you are going to see some similarities. And I'll mention that as I'm going through titrations when we're looking at those titration curves, because there are some points that really make this a lot easier. All right, so I'm trying to find Ka, so I can rearrange my log. If I just have Ka is going to be equal to 10 to the negative pKa, just like H plus is equal to 10 to the negative pH. There aren't too many things you have to memorize that are on your equation sheets. This is one of those relationships. I mean, if you think that rearranging a log is fun, you want to do that while you're also struggling through an exam, go for it. But I think this is one of those things that just saves you some time to remember this. All right, so to figure out that Ka, again, it's just going to be equal to 10 to the negative pKa, which was negative 4.76. What does that give me? Let's see. So that Ka is 1.7378. So I'm going to go ahead and round that. 1.74 times 10 to the negative fifth is my Ka. All right, so just a point with sig figs. When it comes to pHs, this is like your magnitude, sig figs and pH. So this is your magnitude, because this is a logarithmic scale. These are your sig figs. So in this case, we only have 2 sig figs, which also matches with our concentration. So we'll want to make sure our answer also will have 2. So this would end up being 1.7 times 10 to the negative fifth. All right, so now let's go ahead and determine that pH of the solution. So now that we have our Ka, we can determine the pH. Sorry, I'm not trying to be sloppy with my handwriting, so call me out in the chat if you cannot read my writing, and I'll try to work on spending more time on that next week. All right, so now I want to determine the pH, and you're looking at this, you're like, how do I even know how to do this? I don't have H plus concentrations. I have nothing. Wrong. You have your Ka. You know how to write out your equilibrium expressions. You know how to write out the Ka expression as well. So it's going to be the concentration of your products over your reactants, keeping in mind that water is a liquid, therefore it's not going to be included. So it's going to be the concentration of H3O plus over your conjugate base, C2H3O2 minus, all over your concentration of your acetic acid. All right, and we know now that that's going to be equal to 1.74 times 10 to the negative fifth. So looking at that, did I have my initial concentration? I did. So this is going to be 0.2. This is going to be equal to x. So we'll say x squared over 0.2. Now we're just doing some algebra. So 1.7 times 0.2. We then take the square root of that. And that gives us that x is equal to 0.00186. And I know I didn't have any units with my K value, but I am going to have units for X because I've just solved for the concentration. What is that equal to? That is my H plus. All right, so we are most of the way there. We now have our H plus concentration. We remember that the pH is equal to the negative H plus, negative log of H plus, sorry. We just plug that in. All right, so pH is the negative log of 0.00186. And that gives me a pH of 2.73. All right, again, so going back to sig figs, this initial number is just your magnitude, so that's not going to count towards sig figs. Just the 0.73 will count towards our sig figs. All right, so what do? We wrote out our dissociation equation. We then figured out our Ka by just taking 10 to the negative pKa. That gave us our Ka value. Then we went out and we wrote out our Ka, or our acid dissociation constant. We looked at the expression, recognizing that X would be equal to the concentration of H plus, and just solving for that. each problem is going to be slightly different. We were given that concentration of acetic acid. We were given our pKa. Each problem is going to be slightly different from there, but if you have this process down, you can figure out however you need to get there. All right, so now let's look at the titration curves. So let's say, I don't know, let's say we're doing a weak acid, strong base titration. And you're thinking, wait, Corinne, how do I know what a weak versus strong acid? Is it based on how dangerous something is? Like, how do I know that? You have to memorize it. So there are 7 strong acids. And the reason you have to memorize this is because you don't want to accidentally say that a strong acid is used to make a buffer. You need to know what's going on with these titrations, right? Because a strong acid, by definition, is one that completely ionizes in solution. So you put hydrochloric acid in solution, it's all going to separate into H plus and Cl minus. You put acetic acid in, and some of it's going to dissociate, some of it's going to stay together. That's all going to be based on the percent ionization. So you can calculate that too. If you need to see that, let me know, and I can plan on doing an example with percent ionization next week. All right, but let's just talk titration curves. All right, so let's say, I'm just going to draw. Okay, let's say we have our pH, we have our volume, titrant. All right, we're doing a, don't judge me, not very artistic. All right, so let's say we are doing a titration right now. I wish I had a burette. I totally set one up for you. But basically, we have our analyte in our Erlenmeyer flask. We have some kind of indicator in there as well, and we are slowly dripping this into that, measuring the volume of our titrant. So typically, you know the concentration of this. This is your unknown. You're mixing those together. You can do something called a back titration, which takes one extra step. But again, this basically is what we're doing. All right, so and then you have your curve. So let's say we're doing a weak acid plus a strong base. So let's say we have, I don't know, potassium hydroxide. We said acetic acid in here, and we're trying to figure out our concentration of that acetic acid. So basically, when you have a strong acid, strong base, your titration curve is very straightforward. You have at 7, you hit the equivalence point where your moles of acid and your moles of base are equal. Super easy. You don't even have a half equivalence point because it is just everything is equal. And again, you hit that neutral pH of 7 right at the equivalence point. With a weak acid, strong base, or a weak base, strong acid titration, that is not the case. But don't fear, it's not as hard as it's going to seem. All right, so with this, we're going to have a strong base. That means our equivalence point is going to be slightly above 7. All right, so we're still going to have a vertical slope where we have our equivalence point. If you were here with me earlier in the session, you know I'm not the best at drawing graphs on my whiteboard, so don't judge me. But I am going to show you like the points that you need to include for this. All right, so we have our equivalence point versus we're also going to have something called the buffer zone. And in the buffer zone is where you have the half equivalence point. All right, and with this is really important because at the half equivalence point, the pH equals the pKa. So if you can remember that factor and you're looking at a titration curve, again, it's just half of the moles of acid and base to get to this equivalence point. But if you can remember that that is where the pH is equal to the pKa, it can save you a lot of time when you're doing the types of calculations we were just doing. All right, let's see. Let me jump back in the chat. I apologize. I've been talking all about this, but thank you all for being here. This is just a weekly Gen Chem office hour. We have about 15 minutes left, but we are here every Monday at 8:30 p.m. If you have just joined and you've missed any of the other sessions, please know that everything is now found on Chegg's YouTube page. And then also, there are 11 of these sessions. So if you're taking Oreo right now and you're like, oh, I missed the days of Gen Chem, come back tomorrow night. If you're struggling with stoichiometry, there's a session on Wednesday. And then there's another Gen Chem session on Thursday nights too. So Chegg is here. They want to help you survive and thrive in chemistry this semester, especially as you're gearing up for those exams right before spring break. I don't know about you. I am counting down the days until spring break. We're expecting a big snowstorm where I live again tomorrow, and I'm just not about it. I am so ready to fast forward. Let me jump into the chat and see. Okay, sorry, I had a question related to what we were just doing. So the pH equals what again? The pH is the potential of hydrogen, just the measure of the hydrogen concentration in solution. So you have the pH, you have the POH. If you add those two together, pH plus POH equals 14. So if you have one, you can find out the other. And the POH stands for the potential of hydroxide, which is that OH minus. So it's just a way we measure those ions in the acid and base solutions. All right, let's see. Okay. Can we go through a simple way to memorize conversions? Yeah. All right, so this was on TikTok. So can we go through a simple way to memorize conversions? I am so anti. I just don't like, I don't want you to memorize anything because you already have to memorize so much for all the other classes. So really the things you need to memorize in chemistry will be like the polyatomic ions. You need to know Avogadro's number. You need to know the molecular geometries, things like that. But yeah, so just a couple things there. But can we go through simple way to memorize conversions? Sure. All right. I'm going to draw myself. My kids are going to love this tomorrow. But imagine you have a mole in the center of your hands. And actually, there are a couple of videos trending on TikTok right now where people laugh about, oh, look, check out my mole. And then they have Avogadro's number. Anyway, imagine you have a mole in the center of your hand. On each of your fingers are all of the different units you need to convert into: grams, moles, liters, formula units, molecules, whatever. So as you move from moles to grams, or if you want to go from moles to atoms, moles to anything, you're always going to multiply. Okay, so really cheesy. But I'm all about mnemonic devices and things like that to try to keep things simple. All right, so if we're starting with moles, so let's say I have 15.2 moles of gold. It's a good day if I have that many moles of gold. And I want to figure out how many grams that's equal to. I'm going to end up multiplying by my molar mass of gold, which happens to be, I have a periodic table on my wall because I'm not much of a nerd, 196.97 grams per mole. All right, so I've set this up, right? I've done the official way to do the conversion, but really, if you remember, I'm starting with moles. I'm going into something else. I'm always going to multiply. If you're going in the opposite direction from grams to moles, you're going to end up dividing. If you want to get crazy and go from grams all the way to atoms, you're going to go grams to moles. You're going to divide by that molar mass. Then once you get to multiply, right, you're going to multiply by Avogadro's number to get to atoms. All right, so just a quick little trick for conversions. All right, it looks like there's a really specific question. What I'm going to do is I'm going to save it. It's like split into a couple comments. So thank you for the person on TikTok who put in that question. I'm going to save that and we're going to do that next week because that's how these sessions work. So keep putting those questions in. We have about 10 minutes left. Whatever I don't get to tonight, I save it so that I am ready to go through this. Again, we'll be here, same time, same place. All right, it looks like we had another question. Yeah, so also on TikTok, following up with this, how to calculate moles and different types of equations and grams, molecules, all of that. Yeah, all right. So this is just one step. Basically, you want to set everything up so that you're canceling out your units. So if you think back to the good old days of just basic algebra. If I have x times 2 over x, and I multiply these two things together, this becomes 2x over x, right? X cancels out. So when we are doing what we call dimensional analysis or with these conversions, that's our goal, is to get all of these units to cancel out. So we're switching from moles into grams when I multiply by these two, typically improper fractions. So let's go ahead and we'll do a two-step calculation. And then I think I have some requests for redox, so we'll do that next. All right, so let's say I wanted to figure out, let's see, I don't know, let's say determine number of molecules of copper, copper 2 chloride in 15.15 grams. I should have made this a covalent compound. Sorry. We're going to switch this up. We'll go with phosphorus pentachloride. All right. So reason I switched this, if we were thinking about this, sometimes the hardest thing is understanding terminology. If you were talking about a single element, you're looking at atoms. Those are your particles. If you're looking at covalent molecules, we call those molecules. So covalent compounds are molecular compounds because they are all forming molecules. And then if you're looking at an ionic substance such as copper 2 chloride, that's known as a formula unit. So all of those, if you don't know what to refer to it as, typically you can just write particles. So if we're thinking about the smallest parts of something, we're looking at particles again. But because we are looking at a covalent compound in this, we're going to call it a molecule. All right, so we want to determine the number of molecules. I'm going to start with my mass that I'm given in the problem. That's where you're always starting. You want to have your unit. You also want to label that so you know what you're looking at. Because if you were watching the session earlier, once you start doing stoichiometry and you start switching between compounds, you got to keep track of this too. So get in the habit now. All right, so we have 15.15 grams of PCl5. So I want to convert this from grams into molecules. Some of these problems are going to be really wordy. I highly recommend underlining the information you're given, circling what you are looking for so you don't lose track of what the problem's asking. All right, so I want to convert from grams. So I'm going to put grams on the bottom. I can't just hop from grams to molecules. I have to go to moles first. So I'm going to go from grams to moles. So I'm going to use the molar mass here. All right, but that's not where I want to end. So I'm going to take moles. I want to cancel moles out. And I want to switch to molecules. And it is so confusing, right? You'd think the abbreviation for molecules would be MOL, but that is mole. So take your time writing these out. It does make a difference. All right, so then here we're going to use Avogadro's number. All right, so I recommend starting with your units and then filling in all the numbers from there. So now I'm going to find the molar mass of PCl5. I don't know what that is off the top of my head. So try to calculate that before I do. Let's see. All right, so that's 208. And if you have a different periodic table, your numbers are going to be slightly different, but that's my molar mass of PCl5. So 1 atom of phosphorus plus 5 atoms of chlorine. And then I want to convert from moles into molecules. In 1 mole, there is always this same number of molecules. That's the beauty of Avogadro's number and why most chemistry teachers have at least one shirt with a mole on it, because it is amazing. It doesn't matter if I'm looking at something with 6 atoms or something with 66 atoms. 1 mole is always going to contain the same number of molecules based on Avogadro's number. So now I've set this up. I've converted from grams divided by grams. That cancels out. Moles divided by moles also cancels out. And I'm looking at molecules. So now you're going to want to go through. You're going to want to multiply by everything in the numerator on top, divide by everything on the bottom. Or you take it step by step. You take 15.15, you divide by 208.224, you take your answer, then you multiply by 6.02 times 10 to the 23rd. Be careful. If this number is in your denominator, make sure to use parentheses. Otherwise, your calculator is going to divide by 6.02 and then multiply by the whole thing by 10 to the 23rd. So take your time to put in those parentheses. All right, so we get 4.38 times 10 to the 22nd molecules of PCl5. All right, so let's just double check that. I should have done one more sig fig based on that initial value. So if you are struggling with sig figs, only worry about that initial value because we're going to assume everything on the periodic table has infinite sig figs. All right, so looking at that, I now have this molecules. If I want to take this one step further and to figure out my number of atoms of chlorine, let's say, I would just add one additional step. So I would say, okay, for every 1 molecule of PCl5, I have 5 atoms of chlorine. All right, so if you're asked to take it one step further, looking at some kind of compound, whether it's covalent or ionic, you just look at the initial, just the one unit, and then see how many atoms you have in each. All right, so thank you for being here. We are going to go ahead and jump from conversions into, we're going to do oxidation and reduction to end the session. And it looks like next week we're going to talk rates. And I think I just had a question come up about first order. Yeah, looks like we'll be doing some rates and rate laws next week. So thank you all for being here. Thank you for putting those questions in the chat. We'll end with just a quick redox. And again, I hope to see you here again next week, same time. And then if you can't make this session, Chegg has so many options to help you out. So check out their YouTube channel. Know that there's an orgo session tomorrow night. There is just a stoichiometry session on Wednesdays and another great Gen Chem session on Thursdays. So check them out. Know that we are here to support you. That's why we're all doing this, because we want to help you. We want to help you feel confident in chemistry. All right, so let's do some redox to end the night. Let's see. We're going to do it in an acidic solution. All right, so with redox, what does it stand for? Oxidation. So it's oxidation and reduction. So it's just the transfer of electrons between different species. So with this, you're going to be pulling out your half reactions and then trying to balance from there before adding those up together to make sure your electrons cancel out. So it sounds overwhelming. Let's go ahead and just start by writing out those half reactions. So with this, we're looking at the species that are changing charges. Really easy to pull out. I minus goes to I2. So now we know it very clearly has a charge of -1. Because it is just a neutral compound, it's going to have a charge of 0. So what's happening in this case, right, is I am gaining or losing an electron. If I go from -1 to 0, I've become more positively charged. It means you've actually let go of those electrons. So this means I have lost 1 electron. But looking at this, we need to balance it, right? So I have 2 atoms of iodine on my product side. I'm going to need to put a 2 here. That means I'm actually going to be losing 2 electrons. So that is one of our half reactions. Now let's pull out the other one. So we have MnO4 minus going to Mn2 plus. This one's a little bit more tricky because we have to figure out the oxidation number of manganese here. The easiest way to do this, right? We look at oxygen. We know oxygen has a charge of -2. I have 4 of those. So my net negative is -8, right? No, because I have a net negative for the compound of 1. So that means manganese has to be 7 plus. So in this case, I'm going from 7 plus to 2 plus. How do I do that? How do I lose 5? You have to gain 5 electrons. All right. So we'd already balanced everything in this first half reaction. Let's go ahead and balance out this one. So with this, we're going to do this in acidic solutions. Just abbreviate. All right. So with this, what we want to do is you want to balance everything other than oxygen and hydrogen first, then go back in, add water molecules to balance out your oxygen. Wherever you add on one side, you'll have to add H plus on the other side, and then double check all of your electrons. So let's go ahead and do that. Let's see. I'll use other colors so you can see. All right. So in this second half reaction, I have 4 atoms of oxygen. So I'm going to need to add 4 water molecules. When I do that, now I've added 8 atoms of hydrogen. So let's go ahead and add those in here. All right, so now the question is, how do I add in these electrons? I've already figured this out. What's the difference here? So in this one, if you are adding electrons are going to be a reactant. Okay, versus if you are losing them, they are going to be a product. Now what I want to do essentially is I want to add these up to equal out my initial reaction. Right now, as written, can I do that? No. So what we have to do now is find a way to make these electrons cancel out. So now essentially what I'm going to have to do is go back in, multiply each of these. The first one is going to be multiplied by 5. So this becomes 10, 5, 10. This one I'm going to multiply by 2. All right, so now I can add those up because the goal is to get the electrons to cancel out. Because again, a redox reaction is all about those transfer of the electrons. So those are going to cancel out. I'm just going to add up whatever I have left, canceling out anything that doesn't add up. Here, sorry, I shouldn't have done that. But we'll just add all of that up, making sure that we have canceled out the electrons. So that is how you balance a redox reaction in acidic solution. So thank you all for being here. I hope the session was helpful. Hope to see you back next week. And keep in mind that Chegg is running a really great promo right now. So if you use the code CheggLive50, you'll get 50% off your first month with